All right. So this is starting from the 25th right now, or sorry, the 23rd. No, yeah, the 25th. So we're going to be starting from the 25th, the lecture of the 25th, and we're just going to be going through explaining some of this stuff. All right. So I think from now on we're going to be talking more about these ester groups. Yeah, you can definitely ask the questions once we're done. All right. So we're going to be moving on to talking more about these ester groups, and so what this is kind of going to look like is he's giving two examples here. So one of them is like this, right? Well, actually, that's not the ester group yet, but so we have this, which is called methonic acid. And so as you know, this is an acid group, and it's called methonic because it only has one carbon in it. And then we have the ethonic one, which is just like this. So this has two carbons in it. And this is just going to be helpful later for knowing, like, I don't really know if you really need to know these names for the exam. We'll see, but I don't really think so. Sometimes he might put like the word methonic acid or ethonic acid in the wording of a problem, and you might have to know what that is for that reason. And then he has one more here, which is just, yeah, anyways. Okay, so, and it can go on like that. You have, you know, methyl, ethyl, butyl, so forth and so on. Okay, so, blah, blah, blah. So, like, as you know, what makes these acids acidic? Like, for example, let's do ethonic acid. So what makes this acidic is the fact that it has resonance. So let's just review real quick what resonance is. So resonance is once the, like, let's say that, because this is like an acid, right? Let's say that a strong base were to come along, OH minus, and it were to grab this hydrogen, right? So after that, what we get is we get an O minus there and the double bonded O here. At this point, what happens is, like, let's draw a lone pair so we can really see what's happening. So essentially what happens is that one of the lone pairs from here, because this oxygen is experiencing a ton of crowding because it has like so many lone pairs around it. So all that crowding causes one of the lone pairs to go and flip onto this carbon in between that bond. So that lets you, and then because we can't have a carbon that's double bonded on this side, double bonded on this side, because this violates octet, right? So because of that crowding on that carbon, then this, I'm just gonna redraw something. This double bond, covalent bond, will go back up onto that oxygen. So what you get is now the double bonded oxygen is here, and there's a single bonded oxygen here with a negative charge. So it's this back and forth between the two oxygens. What it means is that this molecule is better able to handle the negative charge because the negative charge isn't just sitting on the oxygen the whole time. It actually goes back and forth between the one oxygen and then the other, and there's like a ton of like flipping around, and that makes it much more stable once it loses the hydrogen. And before we talked about all of the different things that make something acidic, right? And so those were, I think the first was atom, and then the second was resonance, and then the third was inductive effect, and the fourth was hybridization. Okay, and so like I feel like this might be like old news for a lot of you, but real quick, so atom, that means that it's the it matters about the atom that is attached to the hydrogen that's going to be lost. So let's real quick do the example of NH and OH. So if you compare NH and OH on the periodic table, we have CNOF, and then there's like an S over here, and then this goes Br, No, wait, is this it's Cl, Cl, Br, and then I. So this is just some of your general trends from the periodic table and how they go. So essentially all you have to do is compare the two of them. So first we're going to look at the atoms, so the nitrogen and the oxygen. Okay, well, which one is going to be more acidic? The trends of acidity go this way and this way. So we're going to say oxygen is the more acidic. Now let's compare, I'll draw a line to show that we're comparing something else. Now let's compare OH and SH. So when we compare OH and SH, we're comparing O and S. And between when you're going down the periodic table, S is more acidic. So that's going to be more acidic because, again, we're comparing the O's and the S. Now, moving on to resonance, I just explained what resonance is and how you like figure out if it's happening. Essentially, resonance happens when you have like a lone pair somewhere or double bonds that can move around. Inductive effect, we talked about that last time, but it's like the idea that when you have, let's say that I have this molecule right here, and I'm going to make it like have resonance in it. So this is like one of the markers of having resonance, right? And then I'm going to put myself a Br right here at the bottom. And so this Br is, because it's really electronegative, it's going to help balance some of the negative charge that we end up getting from this oxygen right here. And so when it comes to inductive effect, you kind of want to pay attention to location of the Br or whatever it is. So if the Br is closer, that'll be more acidic than if it's farther away. Another example, if there is, and then you also want to, so I guess number one would be location. Number two would be number. So these are just some tips for figuring out, you know, inductive effect. So if I have two BRs on there, that's going to be more acidic than when you have just one BR, right? So this one's more acidic. So we have location, we have number, and then we have also the type of, right? So some atoms are going to be more inductive than others. And so let's go through that a little bit. So for example, a Br is much more inductive than a, was it Na2 or NO2? Just a second. This stuff can be found about inductive effect can be found on March 23rd's lecture, which I'm going to open up real quick to just review this. Okay, not the 23rd, oh yeah, the 23rd, okay. Oh wait, no, we're already doing the 23rd. Okay, I'm sorry guys. Before that, it's the 18th where he talked about this. Wait a sec. Do you guys know where I saw that? Where did he talk about inductive effect? He like lined up a whole bunch of acids and he said like list them from most acidic to least acidic. You know what, it's probably back here in my notes. Okay, no. Okay, does no one remember the inductive effect ones? Okay, well, I remember one of them was the opposite of inductive effect. So it was Okay, well, anyways, moving on. If we see it, then we'll figure it out from there. But essentially, I feel like I don't even want to say now because one of them was NH2 and one of them was NO2, and like one of them was more acidic. One of them had more inductive effect than the other. Um, so one of them was actually the opposite of inductive effect, and I feel like it was this one that was like completely the opposite. So this one would obviously win because it's a BR. I think NH2 was like NO2 would be most basic. I don't know. Again, like this is just like find that in your notes somewhere. Um, was it NH2 Ollie? I really can't remember. NH2 was the basic one. Okay, so opposite, yes. So NH2 is the most basic, and then NO2 is pretty inductive, but BR is the most inductive. Um, so actually, let me change this for better wording. This is least inductive, and this is the most inductive. And this one, NH2, is like the opposite of inductive. It's not even like it's less inductive. It's like not inductive at all. It's whatever the opposite of inductive it is. So it makes it a super basic thing. Like it really doesn't want to lose that hydrogen. Okay, so let's move on to like some more important things. So after inductive effect, the last thing we talk about is hybridization. So when it comes to hybridization, let's say we have two C's that are bonded like this, and then we have C's that are double bonded, and then we have triple bonded C's. So actually, let me make it a little bit more clear. Let's pretend that it's coming off of the C. So it's CH, or there's double bond CH, or there's triple bond CH. And so this one is, I think this one is the most acidic, right? So this one would be number 1 in terms of acidity, this would be number 2 in terms of acidity, and this would be number 3. So this is the most strong acid here. So that's essentially what hybridization is. Okay, okay. Yeah, so he talks about hybridization, blah, blah. It depends on the the hybridization of that carbon that's going to lose the hydrogen. We usually do carbons because carbons are the ones that can be triple bonded, and like it's kind of typical to use that. Once the hydrogen's gone, we use it like the negatively charged carbon for like substitution. We did that last year. Okay, and so in terms of reactions, just to remind you of the basics, your reactions are going to go towards the side that has the least acidic acid. So if he gave you, like, for example, let's say he gave you this, he gave you this reaction, or it's really like, um, okay. So when we look at these, first we have to identify the acid on each side. So the acid on this side is this, and the acid on this side is this one. And then we just take the pKa's of each side. And so you don't have to know, like if he asks you what's the pKa of water, you probably don't know, or what's the pKa of this what is it called? Ethonic acid, right? You're not going to know the exact pKa of the ethonic acid, but what you're supposed to do is you're supposed to use the basic rules of acidity and basicity that we know. So let's compare the two of them. The first thing we need to consider is the atom. Well, the hydrogen, so in this case, this is the hydrogen that we're going to be looking at, and in this case, this is the hydrogen we're looking at. And both of these hydrogens are attached to an oxygen. So in terms of atom, they're both equal, right? So in terms of atom, they're both equal. Now, in terms of, here's where the resonance comes in. So in terms of resonance, when we look at them, this one is not really going to have any resonance, and this one totally is. So this one is much more acidic. So therefore, we can say this one is more acidic, and this one is less acidic. So after that, what we can do is we can infer that the reaction favors the side that's less acidic. So it would really look like a huge arrow going there and a small arrow going here. Okay, so that's kind of like a question that I'm not sure if he'll bring up, but it's really good to know that a reaction favors the side that's less acidic. Because think about it, acidity is like, what it means is kind of like instability. Like it wants to lose its hydrogens really badly. So if it wants to lose its hydrogens really badly, why would it stay like that? You know, the reaction prefers to go to the more basic side. Someone asked, would this affect solubility? So I'm not sure what you are talking about because I think that was a message from before. Um, but could you like just specify what you're talking about in terms of solubility?
So when you were talking about the side groups affecting the stability of the acidic acid, um, I was asking sort of about other
In
types
terms of
of.
side groups, you mean inductive effect, right?
Yes, yes.
Okay.
I was trying to I just made a bunch of fluorinated or not fluorinated halogenated compounds the other day, and I
Mm-hmm.
noticed that some of them had carboxylic acids, but when they had really like for example 2,6 diodo not phenol acetic acid,
Yeah.
uh, it was no longer soluble in diethyl ether, dichloromethane, or methanol, and I had to use ethyl acetate. It specifically changed its solubility.
Interesting. Actually, in terms of solubility, that's really complicated.
Okay.
But I think that yes, it does affect your solubility. Now, this isn't really like an acid type question, I think. Because here you're dissolving it in more like organic compounds, that I don't really think are going to react in an acid-based way. I could be wrong about that though. But
Okay. Thank you.
in terms of solubility, yes, if you add certain things or anything, it could change which ones it's going to be more soluble in, and that has to do with like obviously your intermolecular bonding and stuff, and how it interacts with the solute. But that's really complicated, and I don't think he'll ask something like that in this class. Um, but yeah.
Okay.
Yeah,
Thank
he
you.
definitely won't ask something like that in this class. But the main part to take home is that the more like halogens there are, the more inductive effect it is. So the more halogens, the more acidic it is.
Okay. Thank you.
Okay. Um, okay. So moving on, he starts talking about, okay, how do we get carboxylic acids? I feel like we just did this, but let's go over it one more time. So how do we make carboxylic acids? So the first method, which we already did last year, is to have you have a benzene ring, and essentially any benzylic hydrogens will become carboxylic acids. Or actually, no, sorry. Yeah. That's what it is. Um, so KMNO4, um, all it does is it turns that into an acid right there. So this becomes CO2H. So, um, like just to give you a little bit more examples of how this works, it doesn't have to just be a methyl. Like it could be like a chain, and then you could also have like this, right? Whatever. Either way, what it will do is it will literally take both of those and just chop it off and put a CO2H on them, right? So here goes the CO2H, and there goes the CO2H. Um, so this is one way of making carboxylic acid when you have a benzylic ring. Um, Second, we're going to go from an alcohol to a carboxylic acid. And so for this one, again, you just need your primary alcohol, so an OH like this, and you just do Jones. And that gives you, just think of it like I like to think of Jones on a primary alcohol as like just rewrite the original thing, and then all you do is just add a double bonded ketone right there. That's how I like to think of it to make it a little bit easier. Um, and then another function of Jones is so in this case you saw it adding a carbonyl on it, but we can also have the exact same thing. The example he gives here is like um well, I mean, it doesn't really have to be this, but let's just basically, if you have an aldehyde, so like this, just think of it like Jones doing the exact same thing. You just redraw your aldehyde, but instead of that H, you put an OH, right? So I like to think of them as the opposites. Like this one, you just added here, I'll color in red so it'll be more obvious. In this one, you just added a carboxylic acid. In this one, you just added an OH. So it's kind of like similar functions on both. And in terms of Jones, I can't really fully remember the formula for Jones, but you should know it because sometimes he says Jones, but then other times he'll just put the actual formula for Jones, and then you have to like know that it's Jones, right? And as a good point up here, this KMNO4, you can also put K2CR2O7. I think KMNO4 is much easier because it just like rolls off your tongue better, but you should know the K2CR2O7 in case it ever shows up on the exam. And then we also, just to remind you about your other like ways, we also have the halide one. So this is the one where we end up doing essentially a Grignard. So if I have like a BR here, then I can react it with Mg ET2O2, or yeah, ET2O2, whatever. And also you can react it with CO2. So basically what happens is that, and then you also obviously need your H3O plus there. But what happens is that once you have a Grignard and react it with CO2, it literally just makes a carboxylic acid. And it literally, it makes so much sense because, you know, if you draw it out, like it's exactly what you would expect. Okay. And then on top of that, we also have the CN method. So this is what last Wednesday, but we also have the CN method. So if you start off with a halogen, for example, let's just do a BR one more time. So what you can do is you can do an NaCN or DMSO. You don't really have to do the solvent, I think. So what that does is it just changes this to a CN, right? So it literally like this, you know, this is a spectator ion, the sodium, and the CN just comes and attaches right onto where the bromine had been. It's a substitution. After that, how can we get from CN to an acid? You just do H2O and H2SO4, and it literally becomes an acid. Okay. So this one is a really, really important one that people don't really see it right away. But you can think of it like this carbon is the one that's staying here, and it's the carbon on which we're going to anchor our acid, okay? The nitrogen goes away, and we get two oxygens out of here and here. So the water and the acid, the acidic solution are going to contribute to those oxygens to make it into an acid. And then there's one final method, which is also very similar to the one above. So let's say you started off with a double bonded O. You can also change the double bonded O to a CN, and you can just, again, NaCN. And what happens is that this is going to create this with an OH and a CN. So again, the CN is just going to come and attack that carbon. It's a substitution method. But in this case, it's not fully replacing, like the bromine protonates off. The OH is not going to protonate because it's not a good leaving group, like the bromine is. And then after that, we're going to react this with H2O and HCl. And so if you react this with H2O and HCl, this literally turns the CN, and it's literally the same thing that we just did above, right? It literally but it's a little different because it has HCl, but it turns, so the OH remains there, and it turns this into a CO2H, an acid. Okay, are there any questions about all these methods that we just talked about? So we kind of started back at the beginning with our KMNO4, and then which just, if you have like a benzene ring, it's useful. And then we went on to Jones, the two ways to make a carboxyl or an acid from Jones. And then after that, we went over the Grignard methods with the CN, the Grignard method, and then the CN method. There's two of them. Okay, are there any questions about these methods of making carboxylic acids? Okay. Okay. So yeah, I think that's it for this lecture, really. Um, I do want to go back to talk about real quick something that we talked about last Wednesday, and I feel like maybe like no one asked for me to record it, but I feel like it's really important to just like discuss like exactly how it works and stuff. Um, so essentially we're gonna be talking about like intermolecular esters. Um, and so there's kind of like two types of intermolecular esters. There's your gamma or yeah, your gamma esters and your delta esters. So a gamma ester is all you do, because this is going to be really important when we talk about it in a second. A gamma ester has like one, two, or sorry, this is a delta then, 3 and 4, right? So it has 4 carbons in between, alpha, beta, gamma, delta, right? And then the delta one is just going to have the 3 in between. So it has alpha, beta, and gamma, right? So these are the two types of intermolecular esters that we're going to be talking about. And why is this important? You'll see, because there's some reactions we're going to have to do where it like has to go to a specific carbon in there. So again, just keep in mind we have alpha carbons. So this is just for intermolecular esters, right? We have the alpha carbon, we have the beta carbon, the gamma carbon, and in some cases we're also going to have a delta carbon. Okay. So now I'm moving on to March 30th, I believe. Yeah, March 30th. Okay. So I think here we're going to be continuing to talk about. All right, we'll see. Anyways, so there's some like naming stuff at the top, but we'll talk about that if it needs to come up. So these are carboxylic acid derivatives, which means that we can change carboxylic acids into all of these things. All right. So there's an acyl chloride, and what that'll look like is just this. You guys have seen it before. This is very useful for like when you're doing acylation on maybe like a benzene ring or something. Then there's the one where it's the two of them like this. We're going to be talking about how to use all of these different reactants soon, and also how to derive them. So here's just the list of all of them. It kind of like he's showing the reactivity right now. So in terms of reactivity, like sometimes he's for reactivity questions, sometimes he's gonna ask you like he'll give you maybe like a molecule that has more than one of these, and he's gonna ask you essentially where does the reaction occur, and so it'll happen at one of them more likely than the other if it's more a reactive site. Or he'll just list a whole bunch of them and ask you to list them in terms of, or like number them in terms of reactivity. So this is just the essential layout for how reactive they are. So in terms of like looking at them, I like to think of, so this is like the weakest one, or the least, sorry, the most reactive one, and this is the least reactive. Here, let me most. And in terms of going towards the most, I like to think about the idea that the more carbonyl groups it has, the more reactive it is. So that would explain why this one has like 2 carbonyl groups. But then being directly next to a halogen, it makes it more like way more reactive, which is why we use that one so often. So having a halogen is really, really important. And if you remember, NH2 is like the opposite of a halogen. Like everything that a halogen does, NH2 does the opposite. So where did this come up? We were talking about how inductive effect works. And so Cl is like very good at inductive effect. NH2 is like the opposite of inductive effect. So that's why you can think about like what's right next to the oxygen. Is it a halogen or is it like NH2? And then after that, we can just look at like the numbers. So this one has like 2 carbonyls. And then this one has an S and this one has an O. And like remember, S's are more like susceptible towards like because they have like a greater bond length. If you remember like our acidity idea, between oxygen and sulfur, sulfur like prefers to like break away from things the way that it breaks away from hydrogen more easily than oxygen. So I think that makes it much more reactive because when something attacks here, then it can just like break off that sulfur more quickly. So yeah, so that's just a breakdown. So first look at your what's right next to the oxygen. Is it a halogen or the opposite of a halogen, or is and then go from there. Um, okay. Um, all right, let's talk about some of these specific reactions right here. So if we have a carboxylic acid, and this is going to be like how to form them. So if we have a carboxylic acid, right? Because again, these are the things that can be derived from carboxylic acids. So the carboxylic acid, what we can do is first we can turn it into SOCl2. Use SOCl2. And this is something that's not new to you guys. We've learned this before. So all that gives us is it gives us the acyl chloride. And so actually acyl chloride is like the main derivative of a carboxylic acid. It's only from the acyl chloride that we can get all of our other things. So an acyl chloride reacting with like this with a gosh, what do you call it? An alcohol can give us this. Okay. So this is this one right here, right? So we're talking about how to derive each of these. And then also if we go from the acyl chloride and we use like this NH2, so it's very similar. All it does is it gives us this. Okay. Or sorry, no, it's not NH2, it's NH. Okay. And then if we do H2O with this, we get back to the original carboxylic acid, right? So it's just a way of switching it back and forth if you need to. And then we can also just go for the we can do this. Basically reacting it with a different, but like a base version. And so all this does is it simply attacks it and you get like this. Okay. And so they essentially attach to each other like you would probably think. Any questions about how to derive all these? But I think the most important thing to remember is when you look at something like this, remember that you can get it from a carboxylic acid, remember that it just takes 2 steps. First, you have to do your SOCl2, and then you can finally get to that step that you want. So I think that's the most important thing here to remember, like that you can even get those from a benzoic acid. Sorry, a carboxylic acid. Okay. I don't think that any of this stuff is really important, the rest of it. Yeah, it's just going off of that. Okay, cool. Yeah, I'm glad to see that you guys are understanding all this. That's really great. Okay, now let's move on to the acid anhydride. So basically what we're going to be doing is we're going to be talking a little more about this guy right here. So, what can this do? How can we use it? So there is actually 3 different things we could do with it that he's going to talk about. So the first one is to react it with another alcohol. And what the alcohol is going to do is it's like, just think about like how you would expect it to do something, right? It would essentially like attack these, that would break off, right? This would come up, come down, whatever. And so we'd be left with one of these on its own, and then also whatever the product of these two being combined together. Oops. So let me just erase all that and show you guys what the product is that we get. So the product is going to be, it's this, and also we're going to get the other side of it. Okay, so here I'm just going to do some quick little colorings to make sure that you guys understand what's going on here. So this part right here ends up being this part right here. And then this over here is what's over here. And then essentially the green part that I'm going to do right here is coming from this. So that's exactly how the breakdown goes. That's where each of the oxygen goes and stuff. Okay. Also, so what's the next thing you can do with this? You can also react it with something that has like an NH2 on it. So when you just do this NH2 one, it's literally like the exact same thing again. So all that happens is that you do this and 1, 2, and then also, yeah, it's literally like the same thing. Okay. Then, finally, with H2O, we can go back to carboxylic acids, which is very similar to what it did with the, remember the acyl chloride when we did H2O, it just became back to a carboxylic acid. So just remember that H2O tends to reverse these processes. So in this case, we're just going to get both of these. So it kind of just broke off. We have, we're starting off with, oh, I can't do the colors anymore. Okay. Well, anyway, so yeah, we just get the two of them. It essentially breaks it in half. So then there's some practice with that, guys. Obviously, like for example, here, this alcohol, right? It's not always just going to be like this. It could also just, it could be like, like that, right? It could be a phenol, right? It could be anything. So I'm just giving you examples, but it's the functional group that really matters. Then there's a mechanism for how to hydrolyze an ester, which essentially means how to go from an ester back to an carboxylic acid. So as we talked about, water, or like probably more specifically the acid within water, tends to just turn things back to carboxylic acids. And so that mechanism right there, you have to learn that mechanism. So I think so far we have, and that's an acid hydrolysis of ester, and then we have a base hydrolysis of ester. So I think so far we have about 4 mechanisms you need to know for this exam, which is a little bit high because we're used to only having to do like 1 or 2 because, before we were dealing with NMR and retrosynthesis and stuff like that. But yeah, I think we have about 4 mechanisms we need to know. I think the hydrolysis, these 2 hydrolysis of ester ones, and then I can't really remember what the other 2 are, but there's about 2 more other mechanisms you need to know. Whenever you go through the notes and you see like a big page that has like a mechanism drawn all over it, you need to know that mechanism probably. Okay. What's next? Okay, so this is hydrolysis of an ester, like the actual mechanism that happens to it. So, it can happen either in an acid or a base. Oh yeah, saponification. It's a funny word, saponification. But anyways, so we're gonna do first there's the acid one and then there's the base one. But essentially what happens is that you have an ester, right? Let's just say I have an ester, a basic ester. And all you have to do is, like for the basic one, this is NaOH, H2O, and H2SO4, groups to SO4. And all that does is it literally just changes it back to a carboxylic acid. And we also have on the other side this OH, this alcohol. And so the acid one is literally just going to do the exact same thing. You end up with the exact same thing, but you're just going to use, ooh, wait a second. That was an acid one. Interesting. Okay, I feel like this one's, is this one base catalyzed or acid catalyzed? I think either one. I don't know, because like this is clearly a base up here, but then this is an acid down here. I don't know. But either way, the mechanisms are different, but the outcomes are not, they're exactly the same. You just draw the carboxylic acid at the end. And I think whether you do it with an acid or a base is really up to you. So I would just go ahead and use this one if you need to do it for a retrosynthesis. Okay. What else do we have? Okay, there's a few more things. Now, why am I putting this, why is this being put separately? Because we're no longer talking about how to form carboxylic acids anymore, but some mechanisms you need to know with involving these molecules. So the first of them is when you use NH3. Ooh. Okay. NH3. And the second one is when you use aniline. So when you use NH3, and aniline, by the way, what's aniline? Do you guys remember? This is exam 1. Aniline is this. NH2, right? Yeah. So if you use NH3, then all you get is the same thing that we started off with, and it has NH2 attached. And this really isn't a surprise. And if we use aniline, I don't really know why we have to even go through this, because it's literally exactly what you would expect. If you use aniline, then it literally goes okay. So I think obviously nitrogens, they always like to be attached to 3 things, right? And so I think that maybe the point of Dr. Son putting this in the notes is to explain to you how nitrogen always likes to be attached to 3 things. So if you do an NH3, well, then it can be attached to 2 of the hydrogens. But in this case, it's forced to kick one of the hydrogens out because it can only be attached to 3 things at a time. So essentially, anytime you attach a nitrogen to anything, you might have to get rid of a hydrogen. You just want to make sure it stays attached to 3 things, no more. Then there is, yeah, that's boring. Okay. Now we're just going back to some old stuff, Grignard. I mean, do you guys want me to explain some of that stuff again or no? Some Grignard stuff? It's old, but you guys might have forgotten it, honestly. Because it was last exam for you guys. Yeah, it's not hard to understand. Okay, I'll just quickly go through it real quick. So this first one has it's like this, and you're reacting it with 2 of these. So essentially all you have to do is attack those. This is literally the same thing as this. Just attack that on twice. So essentially what you're going to get is you're going to get one of them, and then an OH, okay? And then after that we have, you know, how does LAH, what does LAH do? So we have like this, whatever. And then reacting this with LAH gets us a hydrogen H minus attacking here. So what's that going to do? It's going to go up, it's going to go down, it's going to break off. So we're just going to get that, right? The primary alcohol. So that's the basics of that. Next, hydrolysis of amines. So hydrolysis of amines. So if we have an amine and want to go back to our carboxylic acid, which we can do, is this the, or amides, okay. That was hydrolysis of esters. Okay, so hydrolysis of amides. So we're starting off like this, and we'll react it with OH minus. What we get is we get this turning into the basic version of a carboxylic acid. So it's literally just that. And then if we react that instead with with an acid, so like HCl, right? So if we react it with HCl instead, we get this turning into an acid. Okay. So it's just like how to get from an amine to an acid, but you can also just get from an amine to the base version of the carboxylic acid. It's really, or benzoic acid in this case, it's really up to you. Okay, so we had already talked about, I hope you guys, like, I went over on Wednesday, but I hope everyone still remembers like what we talked about last time about alpha halogenation. So you essentially and like beta ketone, beta keto acids and stuff. Do you guys remember that? Beta keto acids and alpha halogenation. Anyone else? I just have one response yet. Beta keto acids and alpha halogenation in an intermolecular ester. Okay, I've only gotten yeses so far. So, this is going to be similar. This is a lactam. So a lactam is essentially what you would think of like, it's like it's analogous to a intermolecular ester. It's an intermolecular like amide type situation. So it has an N there instead of an O. And in this case, this is a beta lactam because it has alpha beta carbons. There's only 2 carbons in between. And of course, like, there's going to be some reactions that you could do with that. But, oh wait, he doesn't really go on to any of the reactions, so. But we already talked about amides, like these up here with amides. So, yeah. Okay. So, in terms of names, by the way, like I just want to bring this up because there's a lot of words I'm putting out there, right? I do not really think you need to know all the names of these things. You just need to like look at the structure and know how they react. So, for example, this next section is called 19.17. It's called preparation of nitriles, and I think nitriles are essentially CNs. Um, but like you don't have to know what the word nitrile means. You just have to know that when you have, for example, a Cl and it reacts with KN, then you're going to get the CN being attached, right? Or NaCN, either way. And we already did this one before. This is a simple substitution. So then we also went over the example where, let's say it was a carbonyl, and the carbonyl react with KCN. So what you get is you just get the CN over here and OH over here. It's also just a basic substitution. And then now this one is when we go into the amides. So, or actually, I don't know if it's not considered an amide. I always get confused about the namings for like nitrogen ones, nitrogen-based molecules. This is an amine, I want to say. But if you react it with P4, so this is what someone was mentioning earlier, from the questions that you guys had. So yeah, so this is just a way of turning an NH2 into a CN, P4O10. Um, so this is just stuff that you guys have to memorize. Like I would recommend writing down a long list of like all this stuff and then just, you know, like keep looking over it and like remembering what does this thing do. Okay. We can also go, so once we have our CN in place, we can also go back from a CN. It's crazy. It's crazy, guys. We can hydrolyze CNs as well. So we had just hydrolyzed some other stuff. You guys are probably gonna want to look back at this video if you want to remember all this stuff. Or you might be taking like really scrupulous notes right now, but there's a lot. So we can also hydrolyze these nitriles. So if you have like a CN like right here, all you have to do is react it with like I think you can do it by acid or by base. So if you want to do it by acid, you can just do H2O, H2SO4, whatever, and you're gonna get this being turned into an acid. And then you can also do it with a base, so the same thing, but we're just gonna do like KOH, maybe some H2O. And then I think something that I'm noticing is that you also have to use an acid, but secondarily, make sure it's the second step. Because if it goes in at the same time, you might just get it being hydrolyzed by acid. But you know, if you're doing your retrosynthesis, either one of these is totally fine. Just pick the one you want to do, whether it's acid or base, because they both accomplish the exact same thing. And then finally, we're going to take this CN and we're just going to change it into a carbonyl. So, or actually anything, you're just using this as a Grignard, okay? So how does this work? Let me see. So if you have, this one is interesting. If you have, I'm going to use the example he gave. So if you have CN here, right? And we're gonna react this with MGBR right here. And then regular steps of like ET2O and like H2O or H0 plus. What happens is that you get, this one is actually really, really important. You get this, or no, sorry. Just get that. So honestly, this one is hard to explain the exact mechanism of it. But when this first thing comes along, this is essentially a CH3 minus, right? So the CH3 minus will attack here. Actually, no, sorry. It'll attack here, right? And then that causes the nitrogen to break off. So what you get at that point is you get this. This attached to, oops, sorry, just a second. I'm like confusing myself a little bit right here. You get, oh, yeah. Never mind. This is like, obviously a CN is just a triple bonded N. So only one of these bonds goes back onto it because you need to maintain octet. So you're going to get a double bonded N on the one hand, and you're going to get your CH3 down here, right? Okay, that's how it works, yeah. And then after that, when you do your H2O, that basically cuts off the, so damn, I think I should show these steps in more detail. So let's simplify it a little bit by making it like this. Here. So we're starting again. Okay, so CN. So CN, when you react it with the MGBR, right? What happens is that you get the negatively charged, the CH3 minus attacking this carbon, and this nitrogen, the third triple bond comes off onto itself because that would break octet for the carbon. So what you get is you get this, right? because essentially we've just substituted this one on, and then we've broken one of the triple bonds, the third bond between the carbon and the nitrogen. After that, we have the H2O. The role of the H2O is that it cuts it off, so we end up with, I believe this, maybe? And wait, no, it cuts off this here. Oh, this is NMGBR. Okay, so then this changes it into an N when you have the H2O, because then it has something else to go to, and then the H3O plus is the one that makes it into a ketone instead. Okay, but I mean, all these steps are really like besides the point. The important part is that the important part to understand is that you go from a CN to this, essentially. And whatever else that you had, like if you have like this going on here, that also goes on the other side. Okay. Yeah, so that's kind of that. Now it has been an hour since we started, and I just finished up the lecture from the 30th. So I think we're just gonna finish till the April 1st, and then at that point I'll just be taking questions. Yeah. Okay, April 1st, and then we'll do April 6th on Wednesday. Actually, April 1st has a lot of just practice in it, and we already went over all of these principles. So I would say, yeah, and there's some retrosynthesis. So I'd say, can you practice that on your own? We'll also do this on Wednesday. I'm just going to skip forward. So I'm skipping a lot of April 1st because a lot of it is just practice that I would like you to do on your own. And then, oh, it's all practice. Okay. It's all practice. Let's try some of these review problems before we just get to the questions. So, here's one. Okay, so let's start at the top with question number 1. So here we have OH with that. So we have, what are we dealing with here? We're dealing with a carboxylic acid and a primary alcohol. Together, that's going to give us the carboxylic acid, draw like this, and then draw the alcohol coming off the other side. So that's our final answer. We talked about this, how to form these types of things, how they react together. The second one is a little bit different. This one is between, again, a primary alcohol, but instead this time it's a acyl chloride. An acyl chloride. And it's kind of similar though, like what ends up happening in the end. Just take your acyl chloride, and then you're going to attach the alcohol onto the other side. Yeah. Okay, let me just skip some of these. Okay, here. This one is good though. So here we're reacting this with OH minus. And OH minus, as you'll remember, is a hydrolysis, a way to hydrolyze something. Hydrolyze means to turn it back into a carboxylic acid or the base version of a carboxylic acid. So the conjugate base of carboxylic acid. But since we're using a base here, it's going to be the conjugate base that we're going to come up with, right? So if you use a base, you're going to end up with a base. If you use an acid, you're going to end up with the acid. So essentially, this is just going to be like this. All right. And we also have the other one, the OH here. This one's really good. Okay. So here we're reacting this with a primary alcohol. What's going to happen is that we already talked about this before. The alcohol is going to attack the bottom of the carbonyl. Think of it like a Grignard reaction almost. So what's going to happen is that we're going to end up with this, and what essentially has happened is that this has attacked here and this broke off. So now we have the primary alcohol like that, and on the other hand, we have this that broke off from it. Okay, so these are just some ways to apply the knowledge that we already learned. It shouldn't be too hard. Let's do one. Let me walk you through one retrosynthesis problem, and then we'll ask the questions you have. So this one starts with an acid that becomes this. Okay, so if you think about it, first of all, we're going to have to add a bromine into the alpha position from a carbon, from an acid. So adding it to the alpha position of an acid is the PBr2 thing that we discussed. So basically, and you want to do this before you modify the actual carboxylic acid itself, because this is the best way to do it, the most efficient way. So this stays like that, and we have now a Br in this position, which is the correct position that we want. Now, after this, you see that this is an NH2. Oops, that's supposed to be an NH2. So the only way to get to an NH2 is, I just want to show you guys this. Okay, so the only way to get to an NH, for example, here, is to first get through the SOCl2. So going back here, first we're going to do our SOCl2. And what's that going to do? It's going to change it into an acyl chloride. So instead of being with the OH there, it's now a Cl. Then after that, we just have to attach NH3. And if you think about it, NH3 is going to have to, it's going to end up cutting off the Cl, and then also it's going to have to lose one of its hydrogens to maintain the being bonded to three things. All right. Okay, so can Ollie, you said you had some questions from the practice exam?
Yeah, I have a couple.
Okay, cool. You could go ahead and ask them now.
All right. Let me just pull up my thing.
Oh yeah, no problem.
So the first one was on the first page, number 4.
Mm-hmm. Number 4. Okay.
So for this
mm-hmm.
one, yeah, go ahead.
Oh no, I was gonna explain, but you can just go ahead and ask the specific question if you have one.
Yeah, so this one was like the decarboxylation. You need, I thought he said like one acid assists in like removing the other. That's what I said on his lecture, something like that. But anyways, I said B, and then like it wasn't really clear whether there's A or C on the answer key.
Yeah, that is true. The person circled A and C, and then he left them both circled and just circled one of the other ones. That's interesting. Okay. I'm a little confused about what decarboxylation means. Like,
well, I thought it was like the thing where you remove a CO2H, but you need a second one. So I thought it would have been B and D, but I wasn't really.
you don't actually need a second one. It's I think the beta keto acid question, right? I think we I think when we talked about this last time, I had made the mistake of saying that, but it's actually not true. In the beta position, you just need a ketone. Okay, so in the example that we know is true, we have this, right?
Right.
And so all you have to do, you have to identify an acid. This is the alpha carbon, this is the beta carbon. Does the beta carbon have a ketone? It's beta keto acid, right?
Mhm.
Yes, it does. So that one will undergo decarboxylation, right? For the
Yeah.
other two, can you guys figure out if it's going to be A or B, which one is more correct? Or which one is correct? Is it A or B? You guys can send me in the chat. And Mubarak, I'll get to your question in a second. Okay, everyone's saying A, but I'm pretty sure it's B. So let's go through why A is wrong. So if you look at A, and really that's why maybe you would want to label them if you're still having trouble with this stuff. So if you look at A, this is the alpha carbon, this is the beta carbon. The beta carbon has nothing. Wait, am I missing something? You guys are all saying A. No, I'm pretty sure A is wrong because like this one doesn't have a beta keto at all, you know? Does that make sense to you guys? Okay, cool. And then how come C is actually the correct answer? Because C has it looks like this and then it goes like this. Okay, so if you count these, this is alpha and this is beta, and beta does have a ketone, so that one's correct. So all you have to do is, again, identify an acid, and I think I'm the one who said this on Wednesday, and I was completely wrong. It's not that you have to have two acids. You can have two acids adjacent to each other, but actually it's about having a ketone on the beta carbon from the acid. So you don't need to look for one with two acids. Just look for one that has an acid and a ketone on the beta carbon. Okay, what was your next question from the practice exam?
The next one I had was on N. Or L, my bad, L.
Oh, okay.
So I was just wondering how when you broke it up into H3O plus, you got a OH on one side and then like the NH.
Okay, yes. Okay, so this one is something that I think I don't know if I really explained that well, but when you have oops, okay, yeah. So when you have this situation here, and in this situation we're reacting with H3O plus. So again, this is gonna be our hydrolysis of of uh a ketone. So we need to turn this, because it's an acid, right? We're going to be turning this into the acid form. So the carbonyl stays like that, and we get an OH here instead of an O minus, right? That part you probably understand. But from then on, in terms of the nitrogen and like what to do with it, you should literally wait. Why does it have an NH2 instead of an NH? Huh. They got full points though. I don't really understand why it's an NH2. I would just do an NH because I want to keep the nitrogen nicely attached to three things. So I don't really see why it would have a positive charge in an NH2. So that I can't really answer for you. I think I agree with the person who wrote the answer key that like this seems like a reasonable answer, but apparently Dr. San saying that no, it's an NH2. And I don't really see it because I don't remember that being something that we talked about in the lecture.
Yeah, and that was also like leading me to my next question because it's back to back. On the next one, he did an NH3. So I
Wow.
didn't.
Okay. We're seeing a pattern here.
So I wasn't sure like what was up with that.
Yeah, see, I don't remember this from the lecture just now. Sorry. Okay. Yeah, I don't really remember seeing this in the lecture, but I'm really seeing there's a pattern here, and it's kind of that next question is very like similar. So in the next question we have this. Okay, is anyone listening to this and like you totally know the explanation or you remember this from lecture? Because if you know, then it would be amazing if you could explain. But yeah, so in this situation, again, we're doing the same exact thing. It's even using an acid, which is so similar. So you just turn this into the acid, and then the other portion becomes, he says, an NH3 plus. And even the person who did the answer key said that too. So I really, I trust this one. It seems like maybe you have to have a plus when you break it off, I would say. Like, it seems that when you're breaking a nitrile, or not a nitrile, a amide. God, I can't remember if this is an amide. Yeah, when you're breaking like an amide, it would seem that you have to keep this nitrogen to have a positive charge. So whatever it takes in terms of how many hydrogens you end up adding. Or maybe, yeah, I don't know. I don't know. Do you have any other questions though?
No, that was the last one.
Okay, cool. And then Mubaraka, you had some questions as well. You said you have questions from April 1st, page 3. Which one is it?
Epilepsy drug?
The epilepsy drug, the
Yes.
retrosynthesis.
The only question is that 1, 2, 3, 4. It goes from 4, the only 1 degree high OH. But PCC, does PCC add another carbon?
Damn. You're so right. Yes, he shouldn't have done that.
But then I understand that it could be a mistake because in the next step,
Yes,
there's
it has.
I
Yeah,
understand now.
that is definitely a mistake. PCC does not add a carbon. Really, the only way to add a carbon in this situation
CN.
would, yeah, CN, or you could do like a Grignard.
Yes. With the
But
double bonding.
exactly. So, and then you're right. Like at the next step, he goes back to the right amount of carbons that he should have had. So yeah, that was probably just a mistake.
Yeah, I do understand. Thank you so much.
Do you have any other questions?
No.
Does anyone have any other questions? Okay, if no one has any other questions, I'll stick around. But honestly, we can end right here because we do have whatever we didn't take a break today, and we also usually end 10 minutes, 15 minutes early, anyways. So I'm here if you guys have any questions.
Okay, thank you so much. So should I sign out right the next is right now or just leave it?
I'll just sign them out at 8 because that'll just be convenient when I finish my shift. But I'll end the recording too, and then I'll just wait here if you guys have any questions or if you guys want to talk to me about anything.
Oh, okay. Thank you.